Hi everyone, in this section we're going to talk about quadratic functions. A quadratic function, sort of like quadratic equations, is one that can be written in the form f of x or y equals ax squared plus bx plus c. And specifically, if it's going to be quadratic, a can't be 0. If a is 0, it's a perfectly good function. It could be linear. If a is 0, here, let me just delete. If a is 0 but b is not, then it's linear. If b is also 0, then it's constant. But we're interested in that general ax squared plus bx plus c, where the a is not 0. So I have no problem if the b and c are gone, but I do have a problem if the ax squared is gone. To get us started, we specifically want to look at the graphs of these things. So I want to start with a simple version. So I'm going to shut this off. This is standard form. This is really general. All quadratics can be written this way. I want to specifically look at probably the simplest example, which is just plain old y equals x squared. So it is in standard form, but our a is 1, our b is 0, and our c is 0. I don't know why I have this slider. Oh well. Okay, so if we're ever wondering what the graph of something looks like, we can always revert back to plotting points. And remember, if you have the equation f of x equals x squared or y equals x squared, that tells you how to find the points on the graph. The graph is a picture of all the solutions to the equation. So if we let x be 0, the formula tells us that y is always the square of x. So we would just square that to get 0, which means the graph has to go through 0, 0. If x is 1, 1 squared is still 1, so the graph goes through 1, 1. So again, every xy pair that makes the original equation y equals x squared true is on the graph. Boring so far, but 2 gets a little more interesting. If x is 2, y is 2 squared. If x is 3, y is 3 squared. If x is 4, y is 4 squared. And you can kind of see a pattern starting up here. It's never good to just look at positive numbers. In fact, we want to look at fractions and negative numbers and all sorts of things. So let's at least look at some negative numbers. If x is negative 1, when we square it, we're actually still going to get positive 1. If x is negative 2, when we square it, we still get positive 4. And I'm going to scroll back up here. If you look at the equation, notice we're never going to get a negative y value. 0 is the smallest thing I can possibly get when I'm squaring, because anything else will end up being positive. Yeah, just a couple more. Negative 3 gives us 9. Negative 4 gives us 16. Okay, and I think we're getting a pretty good rough shape going here. I do want to point out something interesting. Ignoring the positive and negative, when you take a number bigger than 1, like 2 or 3 or 4, and you square it, you get an even bigger number. So if you think about y equals x going through here, notice these y values are much bigger because squaring them is making them grow bigger. That's not true of all numbers, and you might not realize this if you don't think carefully. For example, if you plug in 1/2, when you square 1/2, you actually get 1/4, which is smaller than 1/2. So for little values between -1 and 1, you're actually going to fall below that straight line y equals x squared, which gives us this nice rounding out at the bottom. It just doesn't come in and make a point. It makes this nice, smooth, rounded shape. Let me turn it on. So there's a whole bunch of points. If I go back up here and turn on my y equals x squared, that's what the full graph looks like. So that if you plotted every single point that makes the equation y equals x squared true, you get this cool parabola shape. So y equals x squared is kind of this U-looking shape, not really a U, but kind of U-ish, and it is called a parabola. There's some really cool geometric facts about parabolas. I really, for the purpose of functions, want you to have this picture burned into your mind. So whenever you see a quadratic, you're thinking of this picture. They won't all look exactly like this. They can be upside down, they can be moved around, they can be taller, they can be wider. But this is the general kind of starting shape that we always think of. Things to notice, this graph has a minimum. It has a bottom point. It happens to be at 0, 0. That's not true of all parabolas. It's not always at 0, 0. In fact, it's not always a minimum. They can be flipped upside down and then it would be a maximum, but they all have this turnaround point, this turning point. And it has a name. It's called a vertex. So the vertex of the parabola will always be either all the way at the bottom or all the way at the top, depending which way it opens. I would also love it if you would notice that we have a perfect mirror image happening. If you, here, I don't know if that helped or not, but if I put in x equals 0, if I draw a line right through the vertex of the parabola and I look at the left-hand side and the right-hand side, they should always be perfect mirrors. So even if we flip this around or move it, if I draw a vertical line through the vertex, that's called the axis of symmetry. You should have perfect symmetry, perfect mirror images across that axis. So this is kind of the basic foundation I want you to have for all of your graphing quadratics. We know when we see that x squared and there's nothing higher than that we're expecting this parabola shape, and then it's just a matter of figuring out which way it opens, does it cross the x or y axes, where's the vertex, that kind of stuff. Okay, thanks for watching.